This is the commentary for Packet 11 Redox Reactions. First off, the name Redox is actually short for reduction, for read, and oxidation, for ox. And they just kind of combined it together. And oftentimes, instead of saying reduction oxidation, they'll say oxidation reduction. But I'm going to get lazy and just use the term redox reactions. Here's the outline. You need to understand the general theory. Make sure you have those terms memorized. I'll introduce other terms to memorize, but these are the main ones that I can definitely test you on. You'll have to write and understand very, very basic hypothetical half reactions and predict oxidation numbers. Super easy stuff. And then we'll go through the application of redox reactions, which is essentially a battery. So this is an example of a redox reaction. We have a zinc plate placed in a copper solution. So again, your goal is to understand the basics of redox reactions, and then we're going to write these hypothetical easy half reactions and identify oxidation numbers. I may actually have you do some additional stuff by having you predict half reactions, and then understand the basic electrochemical cell, which is essentially a battery. So, going back to the zinc strip and the copper solution, what we're going to go ahead and do is take a look at this right here. This is a zinc strip, and then here is a copper solution containing copper ions. First thing you'll notice is that it's an ion. So it's a 2+ charge, so it's actually missing 2 electrons. And then here we have what we call elemental or neutral zinc. So zinc itself in this situation is not an ion, it's a neutral. So this is what's going to happen in a nutshell. Copper is going to go ahead and gain 2 electrons, forming neutral or elemental copper, and it's a solid. At the same time, zinc is going to go ahead and give off 2 electrons, forming a zinc ion with the loss of those 2 electrons. And those 2 electrons that are given off by zinc is going to be given to the copper ion in order to form the solid copper. So here is my zinc. The zinc is going to go ahead and donate 2 electrons to copper ion, forming a solid copper, which actually then adheres to the zinc plate. And so you'll actually see copper as a orange color as it's fixed onto the zinc plate. And then the free zinc ion is free to roam around the solution. Fancy terms now. Whenever we say that a substance loses electrons, and I'll use my highlighter, loses electrons, we say that it's an oxidation. So zinc underwent oxidation because it lost electrons. So before the reaction arrow, it's neutral. After the reaction arrow, it has a 2+ charge because it lost 2 electrons. Now, the fancy term for gaining electrons is called reduction. So in the left-hand corner, here's my copper ion. Because it's gaining 2 electrons, forming solid copper, then we say that it underwent reduction. So make sure you have those terms memorized: oxidation and reduction. So here's an animation showing the zinc plate, and and it's going to go ahead and lose 2 electrons, forming the zinc cations. Now I'm just going to fast forward a bit. And then here is the copper ions, which are picking up the electrons, forming copper. Now we're going to get into the application of it, the electrochemical cell, in just a second. First, let's go ahead and check out some other redox reactions. Most reactions actually, because they involve the transfer of electrons, are considered redox reaction. There's a combination of losing and gaining electrons, hence oxidation reduction, and hence it categorizes as a redox reaction. Combustion reactions involve the transfer of electrons, where magnesium gives off 2 electrons, forming magnesium 2+. I know it's kind of hard to see, but here is my solid magnesium, and then here is magnesium 2+ as it gave off 2 electrons. And it gave off those 2 electrons to oxygen, which I'm circling now, forming oxide ions. So the magnesium underwent oxidation, the oxygen underwent reduction. So a lot of natural processes involve redox reactions, the transfer of electrons. Everything from photosynthesis to disinfectants. Now, you need to memorize this, so my advice is to memorize this little mnemonic trick. Leo goes grrr. So here's Leo the lion, and he's going grrr. Please highlight that word, grrr. So Leo is loss of electrons, and grrr is gain of electrons. So loss of electrons is oxidation for Leo, gain of electrons is reduction. So here are more examples. Now, this right here that I'm circling is called a half reaction. A half reaction. It just demonstrates either oxidation or reduction. This is a hypothetical reaction. It's not real. So you don't have these spontaneous half reactions occurring on their own. You need a combination of 2 different reagents, each contributing oxidation and reduction for a true redox reaction to occur. You can't just have a half reaction for oxidation only or a half reaction for a reduction only. However, it allows us to visualize and understand this concept, so it's really popular in teaching students. So I'll be testing you on this and creating these hypothetical half reactions. So this is a half reaction for oxidation. Notice here's before, here is after the reaction arrow, and it gave off electrons, so it's oxidation. This right here is a reduction reaction, because here's before, there's the electrons, it's about to be absorbed by the copper ion, and then here is after, it's absorbed and it's neutral. So it's being reduced. It's a reduction reaction. So here are more examples. So in this case, loss of electron forms a sodium ion. Calcium gives off 2 electrons, forming the calcium 2 ion. How can I test you on this? I could actually ask you to write a half reaction for sodium ion. So do a oxidation reaction for sodium. So I could ask you to do a neutral sodium, and then it gives off 1 electron. Keep in mind, sodium normally has 11 protons and 11 electrons. However, because we lost the electron, it now has 10 electrons, which is why it has an excess 1 proton compared to an electron, and it has a positive charge. Um, so another one I could ask you to do is maybe magnesium with a 2 plus charge, in which case you would have to do magnesium, magnesium 2 plus, plus 2 electrons. That's it. So don't overthink this, just write it how I formed. Based on the representative group number, magnesium is in group 2, so it's going to form a 2 plus ion and give off 2 electrons in the process. So that's a oxidation one. I could also ask you to identify. So notice the electrons are on the right side of the arrow, so that's going to be oxidation, whereas the electrons are on the left side of the arrow because it's going to be added into the ion, so it's reduction. So this would be 1, 2, 2. Now, to keep track of the movement of electrons, we have these bookkeeping numbers. So you've all heard of the Dewey Decimal System. Well, a lot of people have. There's something called books, and on books there are these nice location numbers called Dewey Decimals, and that's how librarians are able to find a book inside a library. Well, we have something called oxidation numbers, and those are just like the Dewey Decimal numbers, and the goal of the oxidation numbers is to keep track of the loss and gain of electrons. And this will be important if you take higher levels of science, because we do something called redox reactions where we have to balance equations. And it's not just balancing atoms, but it's actually balancing electrons. We are so not going to do that for this introductory level class, but I'm still going to introduce the term of oxidation numbers. Oxidation numbers that I'm demonstrating to you are going to be super easy. If you have something that's neutral, so I have solid magnesium that's neutral, then the oxidation number is going to be 0. That's it. So if I give you something like this, calcium solid, then the oxidation number is going to be 0. Usually we write it right above the element, but you can write it to the right, depending on how I ask it. If you have a monoatomic ion, such as sodium, then the oxidation number is going to be equal to its charge. So if this is a plus, then the oxidation number right above it is going to be a plus 1. If I have a calcium with a 2 plus, then the oxidation number is going to be a plus 2. The only difference is we simply move the charge from behind to in front, and that lets scientists know that this is an oxidation number. So the oxidation number for a hydrogen ion is going to be a plus 1. That's it. So here are some examples, and that's as much as you need to know. Do they get more complicated than this? Absolutely, because we have to figure out oxidation numbers of molecular or ionic formulas and then apply them in order to balance the electrons on reactions. But this is just to give you a taste of what oxidation numbers are, and that's it. Now we're going to get into the transfer of electrons from a species that's being oxidized and a species that's being reduced. So over here, there's that zinc again, and we start off with zinc solid metals, which I'm going to go ahead and circle, and it's going to give off its zinc atoms by losing electrons and forming the zinc cation, which is what we see here. Now, on the other side, we have a copper plate. And the copper plate in this instance is going to receive these copper ions that are floating around in the solution. There's going to be electrons that are donated to this copper, and it's going to reduce the copper ions, and then it's going to fix to this copper plate. So in the previous example, it was fixing to the zinc, but now copper has its own special unique plate for it to fix to. Notice that this is a reduction reaction that I just circled. So the first one is oxidation, the second one is reduction. You need both an oxidation and reduction to occur in order for a reaction to occur. Now, what we did was we got kind of cool and we split the reaction. So half of it's occurring over here, and the other half is occurring over here, which is where we got the motivation to write these hypothetical half reactions. Now, the electrons that are given off by zinc when it's being oxidized has to come over here to the copper. So this is what we do. We connect up the zinc plate to a wire, and then those electrons are going to travel through the wire, completing a circuit, over to this copper solution. And then it's going to donate its electrons to copper, forming copper solid that's going to stick to the other copper atoms. Now, it is going to result in an excess amount of anions, and nature loves a balance between positive and negative ions floating around in solution. So we have something called a salt bridge, which helps balance out those excess anions and allows the anions to transfer over just so it balances out. But we've essentially made a circuit here. And the cool thing about this circuit is if we were to attach something that electricity can pass through, such as a light bulb, then the electricity can turn on the light bulb. Now, the fancy name for this is called an electrochemical cell, but the common name for this is a simple battery. We just have nothing attached to it. So, the side that oxidation is occurring, that's considered one of the half cells. And then the side that's reduction is occurring is called the other half cell. And it's connected by a wire to transfer of electrons and a salt bridge to help balance out the anions. Other terms we need to get into is anode. Anode is any substance that oxidizes and gives off the electrons. So this is a zinc anode because it's going to give off the electrons. Any substance that reduces is called a cathode. And I'll circle that right there, a cathode. So in an electrochemical cell, you need an anode and a cathode. So be familiar with those terms. Electrons flow from the anode to the cathode, and this tends to be a spontaneous reaction, which is what you need for a battery. So we talked about redox reactions, oxidation, and we talked about reduction. We also have these weird terms. An oxidizing agent is any substance that causes oxidation in another species. So that's a bit confusing, but let's go ahead and go back to this example right here. We said that copper is reducing. Well, we can use another term called an oxidizing agent, because copper, because it's reducing, is causing oxidation in zinc. And then vice versa, because zinc is oxidizing, then we say that it is a reducing agent because it's causing reduction in the copper ions. Not planning on testing you on the term oxidizing agent or reducing agent. I will test you on oxidizing and reduction for sure, oxidation number, and of course the concepts of anode and cathode in the electrochemical cell, along with the term salt bridge. So make sure you know those terms and you're able to apply them. And that is your introduction into redox reactions. And then if you take higher levels of science, then you'll be able to apply those in really cool chemical reactions called electrochemistry. But I'll save that surprise for next class. Next course, not class.